So here's the first three non-trivial terms, and I'm reluctant to go further on this example. I think that suffices. Admittedly, if I kept with my original instructions, I'd be in trouble. I'm missing a term. Yeah. What it is? You look confused.
But like, how did you know that, like, so you said you have the first three non-trivial terms, but you have like more terms up there. So how do you know that those are considered like good as zero?
Oh, I'm not saying they go to zero. They're there. I just didn't write them down.
Then they're trivial. Well, which ones are trivial and why?
We customarily write terms from lowest order. So it's the first three. When we say first three non-trivial terms, we mean the lowest order terms that are non-trivial. So like here, the first three non-trivial terms are x cubed, x to the fifth, and 1/2 x to the seventh. Right? There is stuff above this. We don't, I mean, it's there, but.
Well, like, why is like x squared something trivial?
I'm sorry?
So like, why is something before x cubed trivial?
It's zero. Trivial means zero. Oh, let's see here. Are there other things we can do? There are. So I wanted to, let's see here. Example 5. How about this? One of the other, we'll do more of these some other day. I'm not going to keep doing them at the moment because I think we've kind of reached a saturation point. We should come back to these kinds of examples another day. All right. So I'm going to turn the page here, and this is an example of a geometric series trick. Although I've been told it shouldn't be called a trick, it's a technique, but whatever. So how about this? F of x equals to the natural log of 1 plus x. I want to find the Maclaurin series for this. So I suppose we could just use Taylor series, but I'm going to do it a different way. And so the way I'm going to do it is I'm going to say, okay, well, if I differentiate this, I get df dx is 1 over 1 plus x, right? We all agree? Okay, but 1 over 1 plus x, that's the geometric series result, right? So I can convert that to a series by just kind of working backwards from the result. So this is equal to the sum, n equals 0 to infinity of ar to the n, right? And I'm making the identification a equals to 1, r equals to what? X, not quite. Remember, we have a plus ar squared, a over 1 minus r, right? So yeah, so you're almost right, negative x, exactly. So that's minus x to the n. Let's clean that up a little bit. That's the sum, n equals 0 to infinity minus 1 to the n times x to the n. Now, well, that's nice, but we want to find I'm trying to find the Maclaurin series for f of x, right? That's what we said at the start of this. We're trying to find the Maclaurin series for f of x. Now I've got the Maclaurin series for its derivative. So how do you get back? Integrate, exactly. So if we integrate this, we get, f of x is equal to some constant plus the sum, n equals 0 to infinity, minus 1 to the n over n plus 1, x to the n plus 1. I'm using a theorem that I haven't proved. You guys don't seem too bothered that I haven't proved theorems in here. So I'm going to keep with that way of being. I don't think it helps too much if I prove theorems in here, actually. I think more examples are better than me using time for theorems in here. So that is a theorem that's true, though. You can do term-by-term integration of a power series. That is a known fact of calculus. Now, and so that C is not arbitrary. That C comes from integration, but we can pin it down. See, because f of x is a specific function, right? So let's see here. And I'm just going to clean that up just a little bit. F of x equals to C plus, and can we reindex that sum a little bit? Let's make that go k equals 1 to infinity, and let's let k equals to n plus 1. So n equals to 0 gives me k equals to 1, right? And n equals to k minus 1 under this substitution. So if I reindex that sum, that's minus 1 to the k plus 1 over k, right? X to the power k. All right. Now, we need to figure out what C is. See what C is, what should we do? We can plug x equals to blank into the formula there. What's the easiest x to think about possible?
0.
Yeah, plug in 0. So f of 0. So we get f of 0, which is what? That would be the natural log of 1 plus 0 is equal to C plus. What happens with this series when we plug 0 into it?
0.
Yeah, it's exactly 0. Now, you got to be careful. If your series has a constant term, that doesn't have to go away, right? But this series starts at level 1. So when you plug in 0 into x, x squared, x cubed, so those all evaluate to 0. That series. So, and what's the natural log of 1? It's 0, right? So in this case, the constant is 0. So therefore, we get this wonderful formula that the natural log of 1 plus x is equal to the sum k equals 1 to infinity minus 1 to the k plus 1 over k times x to the k. If I write out the first few terms here, I've got what? I've got k equals 1 gives me x, k equals 2 minus 1 half x squared plus 1/3 x cubed plus dot 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 dot. There's the power series for the log derived by geometric series technique. Yeah.
Does it matter if it's k plus 1 or k minus 1?
No.
I thought you said n was k minus 1.
Oh, I did. I'm sorry. It actually, fortunately, it doesn't matter, but you're right. To be consistent, I should really put a k minus 1 there. Thank you. But it's the same formula. You can always add 2 to the exponent minus 1 or subtract it. Yeah.
So what's R?
What's R? R is equal to, oh, we figured out, eventually we figured out it was minus x. Yep.
So can we try and rewrite things like that, but you just make it negative if it's plus, and if it's already existing as negative, you just kind of keep it as positive?
Yeah, you have to use your imagination. So like if I had, like we did this one last time, we had 1 plus x squared, and we were like, well, that's really 1 over 1 minus a minus x squared, like that, right? So that was the sum minus 1 to the n, x to the 2n, actually, et cetera. Et cetera, that's not a word. Okay, so this example, what happens when you plug x equal to 1 into it? Then we'll call it a day. like I said. I told you guys the alternating harmonic series converged to log 2. Here's proof. Yeah. At no point will it happen that I magically derive pi squared over 6 for the p equals 2 series. That will remain shrouded in mystery unless I actually get around to covering Fourier series. You guys know what Fourier series are? They're things like this. You're like, I said no. I said no, you monster. If you had something like this, this would be a Fourier series. It's a sum of sines or a sum of cosines. It's a trigonometric series. The reason they're called power series is we're adding together power functions. So these are trigonometric series. You're adding together trigonometric functions. This is not part of the standard calculus canon as it currently exists. Thanks, guys. Adios, muchachos.